I apologize for ending the recording abruptly. I had an urgent matter to attend to, sadly, so I could not finish the recording, but now we will continue from where we stopped in the search algorithm. So as you can see, we prepared the search algorithm. Now to test it, we actually need to prepare the insertion. This will be the recursive method, and I should set this to private. Here we will simply insert a node. This is the node we wish to insert, so we can call this new node, the one that we wish to insert. Here it will be node root and int data. This will represent the data that we wish to enter. Okay. Here we will simply set this dot root to this. We do not really need this for the methods, and we do not need this either, since there is no ambiguity, but we will leave it regardless. Root and I am sorry, I have to take this. I will return shortly. Apologies for that. I have returned. And I realized here I made a mistake. Here will be the new node as well. Only for searching do we pass in the data. For insertion, we will be checking with nodes. And here we will pass the new node. So what do we need here? Firstly, we need to check if the root node is null. To remind you, if I have this structure like so, then we have this node, and then we have these two nodes. This node here, this is the absolute root node for the entire tree, because remember, all trees have a single root. I know people may argue and claim that there are different branches for the root. I understand that, but I am referring to the foundation itself. Every tree has a single root, as in a single foundation. But if we decide to isolate this portion of the entire tree, this becomes a sub-tree, where this is the root node of this sub-tree. So technically, every node that contains children is considered a root node. The only question is if it is an absolute root node, which is the beginning of any tree, or a relative root node, which is the beginning of a sub-tree. Leaf nodes, these ones here, these are not root nodes. Why? Because they do not have any children. Unless you will add or insert children nodes for them, then they behave as root nodes. But if this is the full tree, this structure here is the full tree, and you will not be adding anything to it, then these are not considered root trees. They are considered root nodes, sorry. They are considered leaf nodes because they do not have children. Okay, let us return here. So firstly, we need to check if the entire tree is present or absent. So we are currently checking for the absolute root node. If this root is null, then if this tree is absent, it does not exist, let us say we have this new node here that we wish to insert into the tree. If the tree is non-existent, then we should make this the absolute root node. So that is what we are checking. And remember, here we are passing the root node of the binary search tree as an argument. So we are checking to see if this is null or not. If it is, that means the tree does not exist. Then root is equal to new node. And that is it. This means the new node that we wish to insert will serve as this spot right here if it is null. If this structure does not exist, this will become the root, the absolute root node, and then we can build off of it. So this new node becomes the root node of the binary search tree right here. If this is true, then we need to assign the position of this new node. If I delete these, for example, and I delete this. Okay. Now I wish to insert this new node into the tree. Firstly, is the root node null? No, it is not, because it exists. It has space in memory. Then there are only two locations for this, because it is a binary search tree. We either place it on the left-hand side or the right-hand side. What determines the path? The data contained within the nodes. Let us say here is 10. And this one contains 7. So now we will compare the contents of this node with the contents of this node. If this is lesser than this, we will put the new node to the left here and connect the two, obviously. If this is greater than this, we will move the node here and connect it here. Obviously 7 is lesser than 10, so it will belong on the left-hand side like so. If new node dot data is less than root dot data, then place it on the left-hand side. What is the node for the left child? It is this part here in our node class. This means the child node that is to the left. This is the child node to the right. So we wish to place this to the left, which means that we will take the root node because we are beginning from here, and then we will choose left of the root node or right of the root node. So it will be root dot left is equal to what? Begin this again. Remember, we will resort to recursion because we have to check at every level of the tree whether there is a level that exists, and if there is, should the newly inserted node be placed on the left-hand side or the right-hand side at every single level. Then root dot left and then new node. So now this becomes the relative root node of the new subtree if it exists. So this means here this will now be root dot left, which means that this will be root dot left is equal to null instead of root, and then it will be root dot left root dot left is equal to new node. When we reach this part and begin the recursion, this is what will be compared instead, like so. Now, is there a node at the left hand side here? Is this null? Yes, it is. So set the left node to the newly inserted node, which is this one here. And then connect it like so. So now this has become part of the tree. So I will remove this. Actually, Control Z. Perfect. Else, well, what if the data contained in the new node is greater than that of the root node? I will use a different color here to represent a node on the right. Let us say I will add 15. Again, exact same process. Is there a root node here? Yes, there is. Okay, let us compare the contents. This is greater than this, which means it will belong on the right hand side of the root node. This will be a child node on the right hand side. Root.right is equal to insert node root.right and new node like so. And once everything is done, we will return the root node, which will contain references to its right child and or left child if they are present or necessary. Now, when this part is triggered, this, what will be passed here, will be root.right. And here it will be if root.right is equal to null, and here it will be root.right is equal to new node, assuming it is null. Now this has been designated to be the right hand side through this part here, and once the recursion begins, this will be the new argument, as you can see here. Is there a node on the right hand side? No, there is not. Set the node on the right hand side. Set the child node on the right hand side of the original root. So this spot right here of the original root, root.right. Set the node on the right hand side of the root node to the newly added or the newly inserted node, which is this one. And then return root. So we will add a connection here, and that is it. Once the return statement completes, this is what the tree will look like if we insert 10, 7, and 15. I will delete these because we do not need them. And I will delete this, and I will delete this as well. Okay. Now let us test the search algorithm by testing while testing the insertion algorithm. In the driver class, we will create, I will call it BST for simplicity. Now, let us insert 3 or 4 nodes. Dot insert new node. Did I create the console? Oh, yes. Oh, yeah, I did. Okay, perfect. So let us add 10. Dot insert new node 5. Insert new node. Let us use 15, the same diagram here. And then after that, let us search for 10, 5, and 15, and then choose a number that does not exist in the tree. Now remember, searching returns a boolean, so we can display the output of that return type in a print statement. How should I display this? Search for. Now remember, searching takes the data itself, whereas insertion requires a node. And then within the node, as you can see here in the constructor, we pass the data itself. This part right here. Let us pass 10. So this should be true. Bismillah, let us test it. True, perfect. So that means the insertion logic functions properly. Let us search for 5 and 15 to ensure that this logic functions properly. Because we have tested this, and this is true, because root.data is 10, since this is the root, the absolute root node. Now let us test searching on the left-hand side, so we will use 7, and searching on the right-hand side, so we will use 15 in this scenario. Oh, I will switch this to 7, it does not really matter. Okay. Now bst.search 7, this should also yield true. Let us test it. Bismillah ar-Rahman ar-Rahim. True and true, perfect. bst.search, we have 15. This should also be true. Bi'idhnillah, and God willing. Perfect. This means our insertion algorithm is correct. Lastly, let us test a number that is not in the tree. And that will be, let us use 20. So this should be false. Run. Excellent. Even though we created the insertion algorithm in one lecture, we have proven that it functions properly through the search algorithm. Remember that every node has the potential of becoming a root node if it is in a subtree. These are leaf nodes, they are not root nodes. But if I decide to insert a new node, 5 for example, then they will become root nodes. Why? Because this node must be added to the tree. And since this is a binary tree, we have reached the maximum of child nodes at this level. What does that mean? It means that the next insertion must take place at this level. It cannot be here anymore because we have reached the maximum number of child nodes in a binary search tree. Each node must have a maximum of 2 child nodes. Now this newly added node containing 5 here must be added either as a child to 7 or a child to 15. And that is where this algorithm plays a role, which means that during the insertion, either this or this will become root nodes or parent nodes. Obviously for 5, for this particular node, the 7 will undoubtedly be the parent because 5 is less than 10, so it will be added to the left-hand side, and since 5 is less than 7, it will be added here. I will represent it to try my best and assuage any form of confusion you may have here. And then it becomes part of the tree once the return statement completes. So now this has become a root node, but a relative one. Relative to this one, this is its root, because now this is a subtree or a portion of the main tree. But 10 will always and forever be the absolute root, the foundation of the entire tree. This serves as a root when we add children. That is it. And once we add a child here, this can serve as a parent, and so on and so forth. And that is it for this video, inshallah. In the next episode, we will cover deletion. Then after that, traversal. How can we iterate through a tree? But instead of iteration, we use the term traversal. Then after that, we can display the entire tree, bi'ithnillah, and God willing. I hope this video was helpful and beneficial to you all. Enjoy the rest of your day, everyone. Be safe, take care, and peace be upon you all. Wassalamu alaikum wa rahmatullahi wa barakatuh. اللهم صل على محمد وعلى آل محمد كما صليت على إبراهيم وعلى آل إبراهيم وبارك على محمد وعلى آل محمد كما باركت على إبراهيم وعلى آل إبراهيم في العالمين إنك حميد مجيد.